Have you ever tried measuring a chemical's volume without a measuring cylinder, or guessing how much mass of a substance to add in a reaction? Without standardized units, it's like baking without knowing what a cup or a teaspoon means chaos. That's exactly why we use systems of units in chemistry to bring precision, uniformity, and clarity to our measurements. In science, every physical quantity, whether it's mass, length, or time, must be quantified using an agreed upon standard. That standard is what we call a system of units. Historically, different systems were used in different parts of the world. Imagine trying to compare experimental data between a chemist using feet and pounds and another using centimeters and grams. Confusion would be guaranteed. That's why chemistry, like all sciences, demanded a consistent language of measurement. And that demand led to the development of unified systems of units. Before the modern era of scientific globalization, three major systems were used across different countries: the CGS system, the FPS system, and the MKS system. Let's start with the CGS system, also known as the French system. It used centimeter for length, gram for mass, and second for time. Then came the FPS system, or the British system, where foot was the unit of length, pound the unit of mass, and again second for time. Finally, the MKS system, often called the metric system, brought in meter, kilogram, and second as standard units. But here's the catch: while each system worked locally, none of them could support the growing need for global scientific collaboration. Think about it. How can a research paper from Germany make sense to a lab technician in Japan if they're using different measurement languages? That's why scientists move towards creating one universally accepted system, which brings us to the SI system. To eliminate the inconsistencies and confusion created by multiple systems, the international scientific community came together in 1960 to adopt a new standard, the SI system, short for Système International d'Unité. This system is an upgraded version of the MKS system but with more depth and flexibility. It defines seven fundamental quantities, each with its own unique unit and symbol. These include familiar quantities like length, mass, and time, but also extend to others essential in chemistry, such as temperature, electric current, and amount of substance. The system even includes two additional supplementary units: radian for angle and steradian for solid angle. What makes the SI system so powerful is its universality. Whether you're doing a titration in a school lab or calculating energy changes in an industrial reactor, you're speaking the same measurement language. That's the unifying beauty of the SI system. Let's now take a closer look at the backbone of the SI system, the seven fundamental quantities. First comes length, measured in meter, symbol m. Then we have mass, measured in kilogram, symbol kg. Time is standardized as second, symbol s. When it comes to temperature, scientists use Kelvin, symbol K, not Celsius, because Kelvin starts from absolute zero, the coldest possible point. Then we have luminous intensity, measured in candela, symbol CD, and electric current, measured in ampere, symbol A. And of course, for us chemists, the most exciting unit, amount of substance, measured in mole, symbol mole. 1 mole equals approximately 6.02 times 10 raised to the power 23. That's 6.02 followed by 23 zeros, particles such as atoms, molecules, or ions. These units are the foundation upon which all other measurements, like pressure, energy, and concentration, are built. Each is like an atom of the measurement world, and from them we construct everything else. Beyond these core units, the SI system also includes supplementary units for angles, radian for plane angle and steradian for solid angle, which become important in wave and quantum chemistry. But what if you're dealing with very large or extremely small quantities? That's where prefixes come into play. Prefixes allow us to scale units easily. Need to talk about a billion hertz? use giga, symbol G. Talking about tiny wavelengths of light, use nano, symbol N. These prefixes attach to base units to simplify numerical expressions. Instead of saying 1000 meters, we just say 1 kilometer. Instead of 0.000001 meters, we say 1 micrometer. It's clean, efficient, and helps avoid a forest of zeros in calculations. In chemistry, these prefixes show up everywhere, from nanometers in particle sizes to megajoules in energy output. They make our chemical language concise and powerful. Let's now walk through some of the most commonly used prefixes in the SI system, both large and small. For large values, we have kilo, symbol K, which means 10 raised to the power 3. Then mega, symbol M, for 10 raised to the power 6. Giga, symbol G, stands for 10 raised to the power 9, and tera, symbol T, is 10 raised to the power 12. On the other end of the scale, we have milli, symbol M, which means 10 raised to the power minus 3. Then comes micro, symbol mu, 10 raised to the power minus 6, and nano, symbol N, which is 10 raised to the power minus 9. Let's take a few examples. A signal of 2.5 GHz means 2.5 into 10 raised to the power 9 Hz. A capacitance of 5 picofarad means 5 into 10 raised to the power minus 12 farads. These prefixes are more than mathematical shortcuts. They are tools that help chemists, physicists, and engineers describe phenomena that stretch from atomic scale to cosmic distances, all using the same system. So, to wrap it all up, the SI system is not just a set of units, it's the universal grammar of science. It allows chemists from different countries, backgrounds, and fields to collaborate and speak the same scientific language. Whether you're measuring how much sodium hydroxide is needed for neutralization or calculating the enthalpy change of a combustion reaction, the SI system is there to bring clarity, precision, and structure. Thanks to its consistent use of base units, supplementary units, and logical prefixes, we can communicate data, calculate results, and build new knowledge without ambiguity. Every time you weigh a compound in grams, record a reaction time in seconds, or express energy in joules, you're relying on the SI system. It's embedded in every lab report, every chemical equation, and every data sheet. I hope this session helped you understand the power and elegance of this system. In the next topic, we'll explore how to apply units in chemical equations and calculations. Until then, stay curious, stay precise, and remember, chemistry begins with measurement.